There are many common genetic disorders caused by long repeats in the human genome. Understanding the genetic basis of the underlying disease biology has been hampered as PCR and Southern blot do not provide sequence information. Despite recent advances in DNA sequencing technology, scientists still face considerable challenges while investigating these long repeats, as they are not easily sequenced. The reason these long repeat regions are hard to sequence is because they require amplification using PCR, which is very susceptible to errors and amplification bias. In addition, these long repeats often expand beyond the read length capabilities of short read sequencing. In general, the longer the repeat in a repeat expansion disorder, the more pronounced the disease phenotype. Without access to DNA sequencing methods that work on these long repeat regions, scientists have been forced to use lower resolution methods such as long-range PCR for shorter expansions or Southern blot for full-length expansion. But what if there was a better way to target these repetitive regions that didn't require PCR, and therefore avoided the bias, errors, and sequencing difficulties of traditional approaches? You've heard of CRISPR-Cas9, a revolutionary gene editing tool that uses short guide RNAs to target a gene-modifying enzyme to specific DNA sequences. Here at PacBio, we've harnessed the CRISPR-Cas9 system for targeting genomic regions such as long repeats to enable full-length sequencing without the need for PCR-based amplification. When we use it in combination with long-read smart sequencing, we can now for the first time get base-level resolution of these previously unsequenceable regions. Now let's explore how this no-amp targeted sequencing method works. The first step is to prepare a sequencing library. Then CRISPR guide RNA is used to target the genomic region of interest. Cas9 cleaves the DNA library. The target region is now enriched for sequencing. With long-read smart sequencing, you are able to sequence the entire length of the repeat region with high accuracy and no bias based on GC content. This is not possible with short-read sequencing technologies that require PCR as part of the sequencing process, since they are both read-length limited and unable to sequence through the highly repetitive regions. With improved tools for characterizing long repeat regions, scientists and doctors are no longer limited by previous technologies. Our no-amp targeted sequencing method can be used to access any part of the genome that is within the reach of the CRISPR-Cas9 system. Additionally, by eliminating the PCR steps, base modifications are preserved so scientists can study things like DNA methylation in a targeted fashion to ultimately better understand gene regulation and function. No-amp targeted sequencing is already having great impact on research into repeat expansion disorders, which is expected to ultimately help scientists develop improved diagnostics and treatment options for disease-causing regions. Just imagine what is possible now that previously unsequenceable regions of the genome are within reach. To learn more, visit pacb.com/noamp.